Alright, well, a couple of people have asked for a couple of examples of shapes of molecules and bond angles, and so what I figure I'd do is just go through a representative list of the different shapes of molecules from memory and an example of each type and how the Lewis structure in VSEPR results in each shape. So the first set of shapes of molecules would be the electron domain geometries. So each electron domain geometry can be a shape of a molecule. And so let's look at those individually. We could have a linear electron domain geometry. And the first example that pops into my head would be carbon dioxide. It might be a really good exercise for you to do the Lewis structure for each of these examples, but if you do the Lewis structure for CO2, carbon dioxide, properly, then you get two double bonds to the carbon, no formal charges, and a nice linear geometry. And what people would often summarize the VSEPR nature of this by saying there's a central atom and two non-central atoms, so AB2, and the linear geometry would be a 180 degree angle. And then if you go to the next electron domain geometry, you get trigonal planar. And so what would be a good example of a trigonal planar molecule? In a previous video I did the dot structure for nitrate, and I'm going to make sure I put the overall charge of -1 and the formal charges of -1 to the singly bonded oxygen plus to the central nitrogen, and there are resonance forms I'm not going to bother to draw in, but in the trigonal planar structure you get 120 degree bond angles. And these are both cases where you have a central atom and a certain number of non-central atoms, but no lone pairs on the central atom. And this leads us to the derivatives of the electron domain geometries, because if everything's atoms, then the arrangement of the atoms is the same as the arrangement of the electron domains. So when all of the electron domains are atoms, then the shape of the molecule is the electron domain geometry. Now when you have lone pairs on the central atom, that's when the shape of the molecule is different from the electron domain geometry. So let me go ahead and think of a real classic for a bent shape. And this bent shape will be based on the trigonal planar electron domain geometry. So in sulfur dioxide, you have a lone pair and two atoms. So the way to think of this, the geometry of those three things, is you have a trigonal planar structure. So that's the electron domain geometry is trigonal planar. But the reason we call this a bent structure is because the lone pair is invisible. So although it pushes the oxygens closer together, it's invisible. So if you just look for the atoms, this is what you see. And when you have two non-central atoms, like in CO2 or SO2, then if there's no lone pair, they can spread out and be linear. If there's a lone pair, that'll occupy some space, push the oxygens closer together, and you'll get a bent structure. If this was a perfect trigonal planar electron domain geometry, then this bond angle would be 120 degrees exactly. But in addition to being invisible, the lone pair of electrons is more repulsive than the bonding pairs and squeezes those a little bit more together than you would expect. So it's three of the shapes you can run into if you see molecules. And oddly enough, another shape that I might list is bent. And you might say, well, you just did bent. And I said, yeah, I did bent already. But this bent is going to come from a different derivative, you might say. So let's look first at tetrahedral. Tetrahedral is one of the electron domain geometries, and if you have methane, CH4, then you have 4 electron domains, all of which are atoms, and the shape of the molecule is going to be the same as the electron domain geometry. Again, with no lone pairs on the central atom, 4 atoms on a central atom, you get the electron domain geometry and the shape are the same as tetrahedral, and the tetrahedral fundamental bond angle is 109.5 degrees. Now, if one or more of these 4 positions is a lone pair, the lone pair will hold the position, but it'll be invisible. So that's where you'll get shapes that are based on the electron domain geometry, but the arrangement of the atoms will be different than the electron domain geometry because the lone pair is invisible. So like in water, right, you have 2 lone pairs and 2 atoms. So in the Lewis structure for water, the central oxygen has 2 lone pairs of electrons and 2 hydrogens. And if I arrange them in a tetrahedral electron domain geometry, I see this. Since the lone pairs are invisible, the shape of the molecule is simply this. So it's bent. And the reason that I listed this bent as different than the other bent is because this bond angle, being based on a tetrahedral electron domain geometry, will only be less than 109.5 degrees, not a little less than 120. So actually in water, this would be 104.5 degrees, because again, these lone pairs are more repulsive and push the bonds closer together. The other shape that's derivative of the tetrahedral electron domain geometry would be Trigonal Pyramidal. And a great example of that would be ammonia. So in NH3, you have a lone pair and 3 atoms on the central atom. And if we draw this more in a tetrahedral type arrangement, the tripod of things with the stick up, then we have the lone pair up here, the 3 hydrogens down there. So you can see the tetrahedral electron domain geometry looks like a tetrahedron when you're including the lone pair, but if you realize the lone pair is invisible and draw the structure without the lone pair, that's why this looks like a 3-sided pyramid, and you get trigonal pyramidal. And I mentioned that this is AB4, 4 non-central atoms on the central atom. For linear, we had AB2, 2 atoms on the central atom, 3 atoms on the central atom. When we have a lone pair, we often label that as an E for electron pair. So this would be AB2E, 2 non-central atoms and a lone pair of electrons for our 3 electron domains, but the invisible lone pair doesn't show up in the shape of the molecule. For bent, we would have AB2E2 would be another bent shape where you'd have 2 lone pairs that are invisible pushing the 2 hydrogens closer together, and then with the ammonia we have 3 non-central atoms, AB3, and 1 lone pair E. So when you have 3 non-central atoms and a lone pair, you get this trigonal pyramidal shape every time. So there's some of the ways we look at the shapes of molecules and how they're related to the electron domain geometries, but not the same. And who wants to guess what the bond angle in NH3 is? Well, if it was a perfect tetrahedron, the hydrogen-nitrogen-hydrogen bond angle would be 109.5 degrees, but since the lone pair pushes the bonds a little closer together, you'd predict a little less than 109.5 degrees, and in fact it's about 107 degrees, if memory serves me right, from being pushed just a little bit closer. So no lone pairs, you get a perfect tetrahedron, and that's the shape of the molecule. A lone pair is invisible, pushes the atoms closer together, down to 107, and then two lone pairs pushing those hydrogens closer together, we go down to 104.5. So there we have the shapes of molecules that you're likely to see in an organic class that all obey the octet rule, and the associated bond angles of those shapes with representative examples and Lewis structures.